मॅम ती उचलत नाहीये कॉल.
Okay, okay. Am I properly audible?
येस मॅडम.
Okay, so now I would like to start. Up till now we have seen the properties of ring. Here again I want to discuss about the unit elements. I hope now you are quite familiar with unit. Let me know what is a unit element. Yes, anyone? What do you mean by unit element? See, we are using two words, unity and unit. So, just can you tell me what is unity and what is unit?
युनिटी म्हणजे मल्टिप्लिकेशन आयडेंटिटी.
Yes, unity is multiplicative identity. Yes, I do agree with you. And what is unit?
ॲडिशनची आयडेंटिटी.
No. Additive identity we always call as zero. We are talking
झिरो.
about unit element. When to say an element is a unit element? In the previous lecture we have seen, if suppose I deal with Z6, then what are the unit elements in Z6? Only 1 and 5 are unit elements in Z6. Yesterday we saw this. So why to call 1 and 5 as unit elements?
हा ते इन्व्हर्टेबल जे ते.
Yes, those elements are invertible. 1 into 1 is 1, we know. So inverse of 1 is 1 itself. And talking of 5 also, 5 into 5 is 1 in Z6. And that is why 5 is the inverse of itself. And whenever a non-zero element is invertible, we call the element as unit element. So 1 and 5 are unit elements of Z6. So I feel the concept you recalled. Now let us move ahead with one more example that we have. What this example says, you see, consider the matrix ring M2Z2. Means they have declared that M2Z2 is a ring. What do you mean by M2Z2? Sets of, this is a set of matrices of order 2 by 2 whose entries are integers. If I fix suffix here 2, if I say Z2, then what will happen? Z2 contains only 0 and 1, as you know. What is Z2? Reminders when divided by 2. So what is this set? It contains only 0 and 1. Remainder when divided by 2 is only 0 and 1. If the number is divisible by 2, we call it as 0, and if it is not divisible by 2, the remainder will be 1. So Z2 contains only two entries, 0 and 1. Now let us deal with the matrices of order 2 by 2 with only 0 and 1 as the entries. What are the possible entries? So all the 4 zeros, 4 places all are zeros. All 4 places are ones. Now you can see only one is there, rest 3 are zeros. How many are such cases? This place and this place. So there are only 4 cases containing single 1 and 3 zeros. Now suppose I have 2 ones. So first 2 places, first row, or then first column, or then diagonal. Keeping 1 in the first position, I got 3 possibilities. Now shifting 1 to this position, what I observe, this one and this one. Okay, because if I handle 1 1, which already I have done, so I won't repeat it. And what else is possible? 1 1 as the column. So with 1 in this position, I mean first row second column position, we got 2 entries, 2 matrices. Now let us move to the third place, that is second row first column. Let's have 1 over here. So the only possibility with 1 here is the last row 1 1. So 2 ones, case when there are 2 ones, only these many cases are possible. Let us count 1 2 3 4 5 6. There are in all 6 positions containing 2 ones. Now let's go to 3 ones. So keeping 1 in this position, I can have 3 ones like this. Again keeping 1 in the first position, I can have this way. Or keeping 1 in this position, I may have this kind of thing. So only 3 possibilities are there. Let me shift my 1 to the next position, that is first row second column. What I observe is only this is the case. So with this, I think we have tackled with all kinds of positions containing ones. Alright, so how many in all I got? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 16. So how many are there? 16. So the very first question said, what is the order of this ring? So order of the ring will be what? 16. What you got? Order means bar. I'll write it in bars. So let me write it in bars. Bar M2 of Z2 so what I got is, yes, what was the number? 16. Okay, and now they are asking you to list all the unit elements. What do you mean by unit element? Those which are invertible. So before going ahead, let me remind you of the multiplication of 2 matrices. How do you multiply 2 matrices? Okay, all are 2 by 2 matrices, means I can define multiplication very easily over here. Number of rows of the first should be equal to the number of columns of the first matrix should be equal to the number of rows of the second matrix. What I mean is, if suppose, just a minute, I forgot to choose this. Okay, so you can have a matrix of order m by n. Can you please help me with another mouse? This mouse is not working properly. Just change it. Wait a minute for this. So I'll try with this mouse. If suppose, no, it is not actually. So I would like to, till the installing is going on, let us see first matrix is of order m by n and the second matrix is of order n by p. What will happen? I can define the product, because number of columns of the first matrix is equal to the number of rows of the second matrix. So the order of the product matrix will be m by p in that case. Okay, now when to say a matrix is invertible, So to go for inverse, I need to first of all talk about the identity. So you just choose a matrix which will play the role of multiplicative identity here. Come up. Which matrix will work as multiplicative identity here?
Zero, zero,
Actually,
zero.
I'm not getting your voice. Hello? So basically we know the identity matrix. Yes, Priya?
Second numbers matrix.
Not able to listen to you, beta.
Second number.
This mouse is not working over here. So, huh? इंस्टॉल होता है ना तो okay, so you can watch over here that I have the identity matrix. You know better that 1001 plays the role of identity matrix. So if I multiply by this matrix to any other matrix, my matrix will remain the same. So you got the identity matrix. Now which of these matrices are invertible, I mean to say? Which of these are invertible matrices? So all of you know, if the determinant of the matrix is non-zero, then only the matrix will be invertible. Then only the matrix will be invertible. So in this case, what do you observe? Is this matrix, first matrix, invertible? I mean 0 0 is not invertible. We never think of 0 matrix. Talking of 1 1 1 1, the determinant will be 0, so this is not there. What about this? Will not be there. So single one will not do. All of these they are not unit matrices. What about 1 1 0 0? That will also not do. This also will not do. This is there. What about this? Determinant is -1 will be there. Okay? This will not be there. This will not be there. Talking of this particular, it is there. This one is there. This one is there. And this one is there. So what you observe? The matrices which contain ones diagonally, whether principal diagonally or off diagonally, they are invertible, they are unit elements, and those which contain 3 ones, they are surely there. So 2 ones with diagonal entries and 3 ones anywhere, they play the role of units over here. Okay, so can you tell me what is the inverse of which matrix? Because that will be our next move. What is the inverse of which matrix? So have to find the inverse of a matrix. Yes, anyone? If suppose I select 1 1 and 1 in this place and a 0 here, okay, what is the inverse of the matrix? If I multiply by it, I need to get identity 1, isn't it? I need to get identity matrix. This is 1 0 0 1. Just a minute. I don't have control over this mouse, that is the problem. Okay. Alright. So I hope you will tolerate this. Now, by what I multiply this row 1 1 here, so that I'll get my first entry to be 1. So, very naturally, I need to have a 1 over here, and suppose I have a 0 here, then it is possible. So, 1 into 1 plus 1 into 0 will surely give me 1. Now, by the first row, I need to multiply over here, so that I need to get a 0. So, yes, can you help me here? First row, what it will be? 0 0 you are saying? Are you saying 0 0 here?
Hey, 0 1.
0 1. So what will happen? 1 into 1, 9. I multiply by the row to the column. So 1 into 0 plus 1 into 1. So this entry will be 1 there, no? And if I multiply by 1 0 here, again I am getting 1 in this place. So that is wrong. That is wrong. So what should I do is, I rub this. I got my fault. This is not possible. So what I'll go to, I would like to move to 0 in this place and 1 here. So what will happen? 1 into 0 plus 1 into 1. I got 1 in this place. Okay. Now I want a 0 here. So what to do? Multiply by, yes, 1 here,
0
0.
0
If you take 0, what will happen? 1 into 0. So you need to have 3 zeros then, hai na? So I hope I'm going wrong somewhere. Would you work out for this? What we feel is, the matrices whose determinant is non-zero, they are invertible, we say. So you need to find out the inverse of that matrix. In our usual case, when I say that matrix is invertible, so in that case we divide by the determinant of that matrix and calculate it. But in this case, we have to find out its inverse from the same set. And here we ought to have entries either 0 or 1. So I hope somewhere we are missing it out. Okay? So we are missing it out. Meaning these might not be invertible in this particular set. Okay? Would you work out on this? So 1110 is not invertible in this particular set, because we want answer back in the set. Okay? So this is not possible. Triple ones will never give you. So what is the only possibility? Only unit elements are 1001 and 0110. So you can see I have to cross this. This is not possible. Not possible. Here also it is not possible. But still you will try for this. As far as the identity matrix is concerned, it is its own inverse, as we know. So only choice with us is 0110 with itself, is it? So what I'll do is, I'll multiply 0110 by itself. See what happens. I hope you might have tried in your book. I'm taking too much time, till that you can complete it. Yes, come up. So what will be the product? Yes, 0 zeros are plus 1 ones are, so I got 1 here. Then I have 0 plus 0, so I got the entry to be 0. Next I go 0 0, so I got 0 here, and 1 into 1. Yes, I got it to be identity matrix. So what I found is 0110 is its own inverse. Okay, and the matrices with 3 ones cannot be invertible in this particular case, because its inverse will not be of that fashion. Okay. Now, going back to our routine knowledge, what is our routine knowledge as far as a general 2 by 2 matrix is concerned? See, whenever you deal with ABCD, this kind of matrix, how do you find its inverse? You find its adjoint and divide by its own determinant. Do you? What is the determinant of this matrix? 1 upon AD minus BC. And you find out the adjoint. In case of adjoint, what happens? These positions of D and A are shifted, I mean interchanged, and this B is just negated and C is negated. This is the inverse of general 2 by 2 matrix. Now, actually I should write here like this. Okay. So now let us deal with the R entry 1 1 1 1 0 here. Okay. So what will be the inverse in this case? If I go like this, inverse will be 1 upon AD means 0 minus BC, it is minus 1, and in this case the position of D will be 0 here, B is negated, C is negated, and A is 1 here. I hope you agree. And now, is it fine? Did you get the point? Okay. Now, this being 1 upon minus 1, so inside what will be its effect? 0 plus 1, this will be plus 1, and this entry is minus 1. So minus 1 itself means it is 1 in Z2. Minus 1 is nothing but 1 in Z2. So 0, 1, 1, 1. So this is the inverse. So I hope you will try for this. What is the product of these two? Okay, I am actually wasting time over here, but still you must have curiosity what happens, and you multiply this by 0 triple 1. Come up. So this will be 1 in the first place. What next? 1 plus 1, 2 meaning 0. This is 1, 0, 0, yes it is 0. And what next? 1 plus 0 is 1. That's fine. That's fine. It is invertible. Its inverse is 0 triple 1. Okay. So I hope this matrix, this one, this is invertible. This matrix is invertible. And what is its inverse? This one. Okay. So this is invertible. So I think similarly you can show that this is also invertible. So hope you will try for this. Okay. So you will try for this, and these are the unit elements. As I said previously, those which contain 2 ones but in diagonal positions, they are invertible, and the matrices containing 3 ones are also invertible in this case. So they are unit elements. So I feel you got the concept of unit elements over here. Do you agree with me? Okay. Alright. So I would like to request you, please note those things down in your own wording. If you have got it, go through the video once again and note it down in your notebook. Alright. I move ahead for the next question. And my next question is, consider the map determinant of Mn of R into R, where determinant of A is the determinant of matrix A for A belonging to Mn of R, is determinant a ring homomorphism? Why or why not? So I think the ring homomorphism you know all better. First of all, let us deal with what are the rings with us. We have two rings, Mn of R. By Mn of R I mean these are n by n matrices with real entries. And by R I mean it's simply set of real numbers with usual addition and usual multiplication. And now we are defining a function. What is that function? Determinant of A. So let us call that function as phi for the time being. What this phi does? It carries A to determinant of A. Extremely sorry for this battar effect. There is no remedy here. Okay. So if you apply phi on this A, output is determinant of A. So will this be a ring homomorphism? Means what? Will it preserve addition? Will it preserve multiplication? Okay. So you have two matrices A and B and you are applying phi on A plus B. Means you are finding out determinant of sum of two matrices. Will it be equal to determinant of A plus determinant of B? Come on. Is determinant of the sum equal to sum of the determinants? The answer is no. Determinant of A plus B is not equal to determinant of A plus determinant of B. This is not possible. On purpose I am using red because determinant doesn't obey this. Determinant doesn't preserve addition. That's why it is not a homomorphism. Okay. And talking of multiplication, what will happen? Is determinant of the product equal to product of the determinants? Determinant of product of two matrices, will it be product of the determinants? So actually if one fails, directly you can say it is not a ring homomorphism. But the question with you is whether determinant preserves product or not. So hope you will think on this, you will work on this, it's important. And I would like to move to the next question. Please note this down. Note this down. An element A of a ring R is idempotent if A square is equal to A. So whenever you have A square equal to A, you call A as what? Idempotent. The square of a number is the number itself. Such number is known as idempotent element. Now the question says, show that the set of all idempotent elements of a commutative ring is closed under multiplication. Show that the set of all idempotent elements of a commutative ring is closed under multiplication. So basically they have given you that we have commutative ring. Commutative ring itself means multiplication is commutative there. And the elements that we are dealing, they are themselves square elements. They are squares of themselves. And you are required to show that this set is closed under multiplication. What you mean by this? If you have two elements A into B, this should be back in the same set. If you choose any two elements A and B, then the product A into B must be there, provided A and B are idempotent. So by idempotent, what I mean is A itself is A square and B itself is B square. Now because it is a ring, multiplication is associative, and it is given that it is moreover commutative. So you can write this as what? A into A into B into B, and I may combine it this way. I may commute it. So what it will give me? AB into AB. I'll use commutativity and associativity repeatedly, so that I'll be getting AB, and it is AB square. What it means? The product of two idempotent elements is itself idempotent, and that is what we are required to show, that it is closed under multiplication, means the operation is binary. And one more example, question B part is given Z6 into Z12, and they are asking you to find all idempotents in the ring. Now Z6 cross Z12 will contain what? Z6 contains elements from 0 to 5. So 0, 0. Then you'll have 0, 1. Okay. Keeping first entry 0, I'm trying to have all kinds of ordered pairs with Z12. So what next do you get? Up to what? Up to what you'll be getting? 0. Please come up. 11. Because we are having Z12, this will be up to 11. Now what is my next entry? In Z6, it will be 1. I take ordered pair with 0. Then 1, 1. I feel you know my strategy. And so on. The last will be what? 1, 11. So this was our second row. And in this fashion, what I'll get? What I'll get the last as first entry 5, 0, 5, 1, up to what? 5, 11. Now what are the idempotent elements means what? If at all you are having, so I would like to rub this AB, otherwise you will be confused. So let me remove this AB. Okay. Now what you observe here, I want idempotent element, means the element if multiplied to itself produces the same element back. So I want ordered pair AB multiplied by ordered pair AB equal to back ordered pair AB. Means I am collecting those elements whose squares are they themselves. A square must be A and B square must be B, because this is component wise multiplication. So in Z6, what are the idempotent elements? 1 ones are 1. I hope all of you know this. In Z6, what are idempotent elements? You have seen this under congruence relation in the chapter of integers. So 1 square is 1, I know. 2 square is 4, so it is not idempotent. 3 square is 9 divided by 6, remainder is 3. So 3 square is 3. 4 square 16 when divided by 6, remainder is 4. So 4 square is 4. 5 square 25 when divided by 6, remainder is 1. So the idempotent elements in Z6 are 1, 3 and 4, as you are observing. Same way you go for elements in Z12. What are the elements in Z12 which are idempotent? If they multiplied to themselves, produce the same result. So let us once again see for Z12. I have 1 square equal to 1, of course. 2 square is 4, will not do. 3 square 9 will not do. 4 square 16 divided by 12 is 4. So I got 4 square is equal to 4 in Z12. 5 square is 25 divided by 12 gives me 1. 6 square 36 divided by 12 is a 0. 7 square 49 divided by 12 is a 1. 8 square gives me 4. 9 square gives me I think 7. 9 square produces 7. Okay.